we're going to consider different models of time complexity, and they differ based on how you define the input size, right? It could be the number of bits, digits, the value, number of objects, or the value itself. I'm screen sharing. I don't know what the, right? We talked about those. And then when we're counting time, we can either count the number of bit operations or the number of sort of value operations. And what I'm going to be arguing is that there are two models that we will consider generally. One when the input's a lot of objects, and the other when the input is really just a few real numbers, integers. All right, so here is the classic example, is the input consists of a bunch of objects, then the input size should be the number of those objects, and the time measure should be, you define what an operation is between values that cost time 1, and you say, we'll let you multiply in time 1. And that's what you were counting. You can decide to count whatever you want to count, but there's an option. And then if you look at what's the time complexity of the usual sorting algorithms, you can get n squared. Right? Everybody good with this model? Yeah. All right, so where are we? Wrong direction. All right, so here's another way of viewing it, is as you can view it as a circuit where the inputs are those objects, the real numbers coming along wires, and then the gates do multiplication or division or whatever, and then the running time is the number of gates while the input is the number of wires coming in, right? One operation that people often forget to count, so I thought I'd stick it in here, is indexing. You have a big array and you want to say, hey, what is the second number in that array? I mean, that's also a task. But we don't want to allow, if we're allowing sort of arbitrary functions of integers, we can't let you do some miracle operation, right? You can't just suddenly solve the halting problem, right? All right, so here's another type of problem where the input consists of two integers or two real numbers, and your task is to multiply them, right? Well, you'll say, well, we've gotten our chosen model of computation, and in that chosen model of computation, the size of the input is 2, and the number of value operations is 1, i.e., all you did is one multiplication, right? So clearly, that's a dumb model for this problem, right? Everybody agree with that? So then let's look at the silliest kind of computation, where all you do is we input some value in and we say hi that many times, right? And here's some example input, right? Then you can say, well, is this a linear time algorithm? What's the size of the input? Well, you could say it's the value is the size of the input. And what's the time complexity? Well, it's the number of times you say hi, right? And so then I guess I've asked you the question, are you willing to say hi this many times, right? Are you willing to execute this problem? And you might say, well, there are a lot of reasonable computations that I'm not willing to execute, and this is one of them. But this one in some ways seems particularly hard, particularly if, I make the number a little bit bigger, right? So there are professors who will say this is linear time, and I'm going to argue that this is exponential time. All right? So here's another algorithm, which we're going to compare them, right? This one, they both have the same input, which is a value, and this one counts the number of digits, which is 15 digits in this, and it says a high for every digit, right? This one says high up to the value, right? And so the question is, what's the running time? Well, one is order capital N, which is the value. One is order little n, which is the number of digits. And you can ask, is the left one linear time? Is the right linear time? Are they the same running time? Clearly, they're not the same. The one on the left feels like it's an unreasonable problem for me to give you to take home for homework, and the one on the right clearly seems easy, right? So we want to think more carefully about time complexity. As I've said, we want to focus on how much work is it for me to give you the input versus how much work is it for you to solve the problem. If we ask how much work is it for you, how much work is it for me to give you the input? Does it take me work corresponding to the value to give you the input? No, I'm not counting out beans here, right? I'm giving you bits or digits. So the work for me is the number of digits in the number, right? Versus what's the work for you? Well, we're going to charge you for every time you say hi, right? So then what's our input size? The input size is either the number of digits or the number of bits, right? And if you compare those, one's the log of the value base 2 versus base 10. Those are within a factor of 3 of each other, so we don't care whether you do base 10 or base 2, right? Now, in the exponential, we can say the value is 2 to the number of bits or 10 to the number of digits. All right, well, there's a difference between 2 and 10 there. But again, they're both exponential, so we don't care, right? All right, so now what's the running time? As we've seen, it's capital N versus little n. But in this top one, we're expressing the running time in terms of the size of the input, which is little n, right? So capital N, we know, is 2 to the little n, right? And in this bottom one, we're expressing the running time in terms of the value. So the running time of the red one is linear, and of the green one is a logarithmic running time, right? Versus up here, the red one's exponential and the green one's linear, right? So you can think which of these definitions seems to make more sense. And I guess the standard is, I wish that would go away. The standard is the top one. All right, everybody buy this? All right, everybody, any questions about this so far? Is that because you were brilliantly awed and amazed, or because you still don't understand? Any questions about it? Yes? Yeah. Where is the login? Here it is. So do you understand how we can define size in 2 different ways, right? And do you agree in this one, the running time is capital N, and this one's little n, all right? So now we need to express the running time as a function of the size of the input, right? You tell me the size of the input, I tell you what's the running time going to be, right? So in the bottom model, we're expressing it as a function of capital N, right? So what is capital N as a function of capital N? Well, it's capital N, right? What's little n as a function of capital N? Well, it's log. Little n is log of capital N. The number of digits is the log, right? And if we were to play the following game where I would one at a time lay out a bunch of pebbles, and then you would take all those pebbles and cut the pile in half and cut the pile in half, right? So your work is how many times to cut it in half, and my work is to lay out pebbles, then absolutely it would be this bottom thing, right? My work is I had to count out that many pebbles, and you had to do log n work, right? But I think that in reality is I write some digits on the board, right? So the work for me is to write those digits on the board. How many digits did I write on the board? It's little n, right? And then if you need to count the digits that I wrote on the board, then your time would be linear in my time. I write in twice as many digits, you do twice as much work, right? But if you're trying to do this one over here, where I write 100 digits on the wall, and it takes me time 100, it takes you time 10 to the 100, dude, you got a bad deal, right? And that's why I'm calling that your work is exponential in my work, right? Because I give you one more digit, takes me one more time, it takes you 10 more time, right? Does that make sense? Everybody else sort of get that? And we're not going to do it today, but we looked at the kindergarten versus, yeah. I'm going to say we crossed that one out. We're not doing that one. We're doing the blue, the one at the top. Yeah, it's. I mean, we want to classify problems about how hard they are. Can we unconfuse you somehow? All right. All right. I guess we want to build classes of problems and be able to compare how hard this problem is to how hard this problem is. Right? And I mean, if I was sort of going to classify problems, I'd say, what problems can you do in linear time? Well, in linear time, in my opinion, is the time it takes to look at the input, right? If all you do is kind of read the input and know the answer, then that's linear time, right? So that's what we're doing in the green algorithm. It's just simply the time it takes to have examined the input, right? Now, you could say, no, there's an integer in my variable capital N, and I just look at it in constant time, right? Well, then you could say it's constant time to look at the input, but that's not our kind of our class, yeah?
this argument begins as problems, since most of them would utilize the complicated operation, so most of them would be that normal and be similar.
No, no. In fact, I would say this simple thing is at the crux of what we're doing, right? So let's look at some more algorithms, right? There's the kindergarten multiplication algorithm versus the high school one, right? And this one, we multiplied A times B by basically counting to B. I guess we added B, we added A a lot of times, right? So that's exactly this. You're counting to the value, right? And what's this one? Well, they're digits, and it's a matter of looking at the digits, right? A little bit more because every digit here has to be looked at every digit here, right? And then you could say, again, we have the high school method for multiplying. And I can take two primes, P and Q, and multiply them together, where I'm just looking at their digits, right? I'm never considering the value. I'm just considering the digits, right? Versus if I want to have P times Q, and I want to factor them and find P and Q, right? There, the only way we know how to do it is to count up to Q. You try dividing in 2 to 3 and 4 and 5, right? So there's a fundamental difference between these kind of problems and these kind of problems. Are you looking at the digits, or are you counting to the value? Right? Yeah. 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 So there's different models, computation, and you're going to get different evaluations in the different models. And I'm making an argument. Maybe you could call it an aesthetic argument, but I'm making an argument for which one we're going for. Yeah. This algorithm here versus this. Oh yeah, the red is the running time of this algorithm, and the green is the running time of this algorithm. Yes, I didn't make it up. A classic thing is to use little n is the size of the input, which by formal definition is the number of bits to write it down. And then if you have a number with little n digits and you need to give a name to its value, sometimes people use X and sometimes people use capital N, right? It kind of links the two. In fact, right, there's one is exponential of the other. Yeah, yeah. Yeah, yeah. Yeah, here 10, the 10 is because I was assuming digits. Yeah. Then it would be 2 to the n. Yeah. Yeah. When I teach 1019, I write both of them as 10 the order n because the constant can get hidden in here. Any other people good with this?
the algorithm itself, right? What should be the criteria of judging other algorithms and changing their input size?
I'm going to give a little, we're going to do different, let me hold off on criteria. It's really not very hard. All right. So now this model up here, I'm saying isn't really fair because I'm measuring the size of the input in terms of bits or digits, and I'm measuring time in terms of value operations, right? So instead, we're going to come over to this one where we're comparing how many bits do I give you, time, input sizes, how many bits I send you. And then your time is how many bit operations you do. We're kind of comparing apples to apples, right? And here's a way of kind of thinking about it. It's an and or not circuit where the input is bits. We measure the size of the input is bits, and you can think this could be anything. You could be solving any computational problem you possibly want. And the input really, in the end, comes to us as bits, right? We're doing this, we're running a computer's in bits. So you send me so many bits, and then I do some calculations, and ultimately, my laptop, it's all AND gates and OR gates, right? So this is the model of computation where we compare the time is the number of gates, right, versus the number of wires coming in. And this model up here is the formal model. If you ask somebody in theoretical computer science, what's the formal model of computation? They would say this: we're comparing bit operations to the bits coming in. Everybody good? All right. So now let's go back to some algorithm like sorting or something, where we have a lot of inputs, a lot of numbers are coming in. And let's see how this model holds up. If it's our formal model, how does it hold up? Well, what's the input? Well, if you want to calculate the number of bits coming in, you have to say how many different values are coming in. And then for each value, how many bits are in that value, and you multiply or add them all up, and you get the total number of bits coming in, right? So that, yes, that is the formal thing to do. And if you're looking at time measure, well, if in your algorithm you do a multiplication, then you have to go in and say how many bits were those numbers and how much did it cost to do that multiplication in terms of bit operations, right? So that's a lot of work, right? It's a lot of work to compute the exact number of bits. It's a lot of work to calculate the exact number of bit operations. And we tend to be lazy, right? So instead, we move down to this model for this case, right? That's what we did when we talked about the running time of sorting to be n squared or n log n, right? We were down in this model. Everybody see that? All right, so then I think this was your question. How do we decide between the two models? Well, if when computing this guy over here, you didn't use the standard, you switched over to the formal, probably it would just be some extra log-in factors in there, right? Because if my inputs are all, if I have n numbers, each of size n, then the number of bits is n log n, right? And then, well, my numbers are of size n, so they have log n bits. And when I do a multiplication, maybe it will take me log squared, right? So the chances are the difference between these two models are a bunch of log factors that we just ultimately don't really care about, right? So it doesn't matter for this kind of algorithm over here. It doesn't matter which one you use, so we might as well use the one that's easier, right? And maybe we'll be, instead of saying it's n squared time, you know, it should be formally n squared with a bunch of logs in there. Maybe, but let's not worry about it, right? Does that make sense? Now, when do you use this one? When do you use the top model? Well, the only time I use the top model really is when the input consists of a constant number of real numbers. And then you have to, what do you really have to do? Everybody knows that they're not going to jump down here and use the number of values because the number of values is 2, and they know that would be dumb, right? So people are used to being over here, and they don't, when that doesn't work, they don't come up here, they tend to come down here, right? And I'm telling you, don't ever go down there, right? Never consider the size of the input to be a value, right? And you'll be good, right? As long as you're not using things as values, whether you use this model or this model will be obvious. All right, everybody good? All right. Was that better slides? Yeah. Why don't you hold on the question for another 5 minutes? All right, because it's going to come up in 5 minutes. Any other questions? All right.